Dr. Dean, when did you say the test was going to be again?
So the test is going to open this afternoon, but we're doing the official review for it on Monday.
Okay.
But
When is it due?
the review is posted online, so I guess I can make a note about that in the chat.
What does it do?
It will be through next weekend, so probably by Monday, probably be due Sunday night, but for the love, please do not wait until Sunday night. Let's see. All right, so as that note says, it will be up sometime this afternoon, and it will be available through next Sunday. But do not wait until Sunday night to start on it, because if you have issues or something, I may not be able to help you. And if you waited that long, then to even start it, I may not be inclined to. So yeah, don't wait that long. Though you do have that available to you if you are feeling extra risky, I guess. So there is a review posted for test number 4, same as previous, but as far as turning it in, extra credit stuff, we're not going to do that this round, but I highly suggest you at least take a look at it, because those are the kinds of things that are going to pop up. There's also some additional review opportunities in WebAssign, so I would suggest checking out your ebook to give a look at those, because they will be very helpful. Kind of with that, remember that due date for all of the homework assignments is coming up, and there's no extensions past that, because I mean they're open, I mean literally as late as we could have them open. So make sure you have been working on those. And let's see.
What did you say about homework?
Just make sure that you've been doing it, because the due dates, remember it's due, I think it's due that same Sunday that test 4 will be due. The idea is it's supposed to be due before finals. And then we're going to spend the rest of next week talking about final exam stuff. So yeah, but we're going to finish off the official learning sections today. And then we will, like I said, do that review for test number 4 on Monday. All right, so let's. All right. So this whole idea of counting that we've been getting into also gives rise to this idea of probability. And the two are very much linked together. So with counting, we were more concerned with counting out all of the possibilities. So you take, all of the things that could happen, and you just say, okay, how many are there? When it comes to probability, what we're looking at is what is the likelihood of getting these different possibilities. So as an example, suppose you throw 2 distinguishable dice and you look at the sum of the faces shown. So what is the probability that the sum is at least 10? Okay. Well, probability is a measure of likelihood, and it's as simple as taking the number of possible cases and the number of specific cases that fit your rule. In this case, the sum of the two is at least 10. And you look at the percentage of, or the ratio of the likelihood that you will hit one that you want out of all of the possible ones. So that's the two basic things that's that are going on here. Is the first one is we need to figure out how many total cases are there. And the second question is how many specific cases fit our rule. So suppose you throw 2 distinguishable dice. How many different possibilities do you have for those 2 dice? So how do we count the number of total possibilities?
And 36.
I'm sorry?
And 36.
So yeah, it's 36. How'd you get 36?
6 on 6 on the.
Yeah, so in the counting, we say, okay, how many events can happen? And in this case, 1 die is rolled and another die is rolled. We look at, okay, what is the possibilities for each event? How many total outcomes could you have? And you're exactly right. There are 6 faces of each dice. Okay. So now we have to look at what is the probability that the sum is at least 10. Okay. Well, let's start from the top. What is the highest number that you could get from adding the two dice together. It's the highest roll you could get. 12, yeah. So you can get a 6 and a 6. All right. Well, what about the next level down? So let's say the first thing you roll is a 6 for all of these cases. A 5 would work. And a 4 would work. Okay. So let's look at the next level down, because 6 and 3 won't work. Well, the first thing you roll could be a 5, and then a 6, and then you could roll a 5 and a 5, but you couldn't roll a 5 and a 4. So that's it. Or you could roll a 4 first, and a 6, but you couldn't roll a 4 and a 5. So these are the only cases that will work. So how many do we have?
Three. Wait. 1, 2. Yeah, 3, right?
1, 2, 3, 4, 5, 6.
Wait.
So there is possibly some confusion here. Some might want to say 4. So you could roll a 6 and a 6, a 5 and a 6, a 4 and a 6, or a 5 and a 5. In which case, you have 1, 2, 3, 4 possibilities. But that's a little bit higher, above our pay grade for right now, is taking into account duplicate possibilities. Things do change a little bit. The way we get around that here is we said 2 distinguishable dice. So distinguishable means the order matters. And so they are treated as different cases. If you roll a 6 and then a 5, is different than a 5 and then a 6. So that might be where the confusion was coming in. But so total we have 6. I don't know, this sounded really 6, we'll just call them good outcomes. So what are the odds of rolling a 10 or above?
Six, right?
So we have 6 ways we could do 10 or above, but we have 36 possibilities. So 36 things that could happen, and we only want 6 of them. So the way we do probability is the number that we want or that we would consider good divided by the total number. And what does that simplify down to?
6.
I'm sorry?
6.
Not 6. close, but it's flipped. Or you might say a 1 in 6 chance. So this is how we do probability. All right. Where's my mouse? So an experiment is a specific action or task that we are considering. The possible results of the experiment are called the outcomes. And the set of all possible outcomes is called the sample space, S, for the experiment. An event E is some sub-collection of these outcomes that fit a certain rule we are considering. The probability of E, denoted P of E, is a value between 0 and 1 that represents the likelihood that the event E will occur when the experiment is performed. So that's big fancy words. Probability space just means it's kind of like it's a math sciencey term, but it very simply means all of the possible, if you think about space you could kind of say is the universe, and it's every possible place that you could be. You can't be anywhere outside of the universe. I mean, theoretically, some philosophy stuff comes into play, I guess, there. But the idea is that you could only ever be in the universe. So the universe is the set of all possible places you could be. The sample space is the set of all possibilities that you could have. So you could never have, in that previous experiment, you could never roll a 15 because there is no way you could add the two numbers you get to get 15. So an event E, some sub-collection of these outcomes that fit a certain rule we are following, like what we just said was the two had to be add to be 10 or more. So probabilities can either be estimated by doing an experiment a bunch of times, but in usual usage, we will assume some theoretical constraints and calculate the probability directly. So one of the main assumptions in this theoretical probability is that things are fair or equally likely. So S be a finite sample space, so you can count the number of possible outcomes. The outcomes of S are said to be equally likely if each possible outcome has the same probability as any other outcome. One way you might think about this is flipping a coin. Theoretically, we assume that what are the odds of flipping heads or tails?
1 out of 2.
Yeah, so you might say 50-50, 1 out of 2. So it's actually interesting, though, that that's not, in reality, the case for a few reasons. One is the heads, I think, is slightly heavier, and it tends to be down a little bit more. We're talking about like 0.5%, but it's not 50-50. The other thing that is possible is that it could land on its side, which, depending on the kind of coin you have, like a nickel, it can land on its side like 1 out of every 150 times, I think. But dimes and quarters are much more difficult to get to land like that. So we assume that none of those random little differences matter in this fair thing. And so if the outcomes of a finite sample space are equally likely, then the probability of an event is given by the number of possibilities for E divided by the size of sample space, which is what we did. We said the number of outcomes that we like, 6, divided by the total size of the sample space, which was 36. So let's try another example. Suppose you are flipping or rolling a die and then flipping a coin. Let's write the sample space for this so what does the sample space look like? Well, let's say, just out of my own personal preference, let's say that we're flipping the coin and then rolling the dice. So what are our possibilities for the coin?
Wait, I don't wait.
It's not,
Say the question again.
it's not a trick question. What are our possibilities?
1 out of 2.
Okay, so you're like moving ahead. What if I flip a coin? What could happen?
Heads or tails?
Heads or tails? All right. So let's do that first one. Let's say we flip a coin and it goes heads. Well, what could happen when we roll the dice? What could happen if we roll the dice? What are our possible outcomes?
Either heads or tails.
No, a dice.
1 through
Die.
6.
Oh, damn, my dumb ass. Damn.
It's early, I know.
Shit. Shit.
What numbers could come up?
6 out of 6.
1 through 6.
5.
So you could get a heads, then a 1, 2, 3, 4, 5, 6. Or you could have flipped tails first, but then your options would have been the same over here. So our sample space has how many objects in it? So remember, each line is an object. What'd you say?
What was the question again?
Got 12. Huh?
How many possible outcomes could you have?
12.
12, yeah. So you can have heads H1, H2, H3, H4, H5, H6, T1, T2, T3, T4, T5, T6. There are 12 total possibilities. Okay? So that is the sample space, is all of those possibilities. So what is the possibility, or how many, I guess, events fit the rule that we're looking for the probability of flipping heads, then 5 or more. So we're going to try and figure out what is the probability of flipping heads and then rolling 5 or more. So how many possibilities fit this?
2,
2. Which ones are they?
5, and 6.
So it would have to be H5 and H6. So T5 and T6 don't matter,
Nope.
but H5 and H6 do matter. So what is the probability of
Would it be 2 out of 6 or 2 out of 12?
So it would be one of those two things. Which one?
Two out of no 1. Wait,
2
2
out
out
of
of
12.
6.
Yeah.
2 out of 12.
So remember, it's just the number of events that fit what we want to happen, and divide that by the total possible events, which is the sample space. In this case, yeah, E is 2, and the sample space is 12, and 1 out of 6. So very good stuff. All right. So kind of with that.
Wait, so the answer was 1 out. So the answer was 1 out of 6.
It was 1 out of 6, yeah, because
Okay.
it was 2 out of 12, but then it simplifies into 1 out of 6.
Okay.
So good question. After we do the fraction, if we can simplify it, we should. Sometimes people will just put it in a decimal form. So, you know, you kind of have to be, or sometimes people put it in a percentage form. Just kind of depends on what the context is. So we also have this idea of relative frequency, sometimes called empirical probability of an event E in a sample space S, is based on the actual experiment being carried out some reasonably large number of times. The relative frequency is calculated the same way. The number of times the event occurs divided by the number of times the experiment is performed. In practice, the theoretical probability that we can calculate will slowly be achieved in the relative frequency when the experiment is performed enough times. This is called the law of large numbers. Example, if a coin is flipped 1,000 times and heads comes up 482 times, what is the relative frequency of getting heads? Note, this number is close to 0.5, but it's not quite there. So what is the relative frequency?
So will it be 482 over 1,000 and then simplify?
That's exactly right. Yeah, it's just the number of times the event happens divided by the number of times you tried to make the event happen. So, yeah, it's just 482 over 1,000, which corresponds to 0.482. So it says, note this number is close to 0.5, but it's not quite there. Anybody who has ever done gambling, I used to be and still kind of dabble in it sometimes. Gambling is a big deal. And this idea of large numbers is kind of at the crux of being good at gambling. So if you take a coin out and you flip it 5 times, you could get a lot of different possibilities. It's possible you could get 5 heads in a row. Well, that might lead you to believe that you have a sample size, or that you have a 100% chance to hit heads. Well, the next one could be tails. The next 15 could be tails. You go on these really funny runs that they just happen sometimes. And so just because it happens 50% of the time doesn't mean that the next time, if it flips tails, that the following time is going to be heads again. It doesn't mean that it flops. It could be heads a bunch of times in a row. But the idea is the more times you do it, so if you did it not 1,000 times, but 10,000 times, the number would be even closer to 0.5. It might be 0.49. But it is very unlikely that it will ever be 0.5. The idea is it will just keep getting closer and closer and closer. And this is the idea of large numbers, is you have to do it a bunch of times to get closer and closer and closer. So let's do an example. If 2 fair coins are tossed, what is the probability of getting exactly 1 heads?
What was the question again?
2 coins, you throw two coins in the air. What is the probability of getting exactly 1 heads? So
50%, right?
So it ends up being that, but let's look at the breakdown. What is the sample space? What are all of the possibilities? Well, you could get heads, heads. You can get heads, tails, tails, heads, or tails, tails. So the event that we want can be done by heads, tails, or tails, heads. So, exactly right. 2 over 4. Getting ahead of myself. %. So here is partially, there's kind of a pitfall to this. Let's look at it from a slightly different point of view. This is only true because we can distinguish the difference between the two coins. So the coin number 1 is in the first spot, coin number 2 is in the second spot. You could run into something that looks like this. You could say the sample space is no heads, 1 heads, 1 tails, or 2 heads. So then the event that we want is just 1 head, 1 tail. Well, what's the probability in this case?
My bad. What's the question?
So we got to the correct answer because we treat the two coins as completely separate. So we flip one coin and then we flip the second coin and they come out like this. Coin 1, coin 2, 1, 2, 1, 2, 1, 2. So, but you may not do that. You might throw them both in the air and say, okay, what comes out? Well, the 3 options are 1 head, no heads. You could look at the 2 coins on the ground, it says, and there are no heads. You could look at the coins and say, okay, one of them's heads, one of them's tails. Or you could say, okay, both of them are heads. So there's 3 possibilities, but only one of those is a possibility that we like. So what is the probability, looking at the thing, in this way? Well, how many?
1 out of 4.
What?
1 out of 4.
Not 1 out of 4, because there's 1, 2, 3 possibilities and 1 event. So you might believe that
1 out of 3.
1 out of 3. But this is wrong. And this is a common thing that happens with gamblers, is they think that these 3 events are equally likely, but they're not. As we saw up here, this one is more likely than the other 2. So we're about to get cut off. I will send out an email reminding everybody and describing the test stuff before it goes up. But yeah, so be on the lookout for that. And I will post all these notes online. Please check those out as well.